For centuries, humanity has gazed at the stars and wondered, are we alone? Is there another Earth out there, orbiting a distant sun, waiting to be discovered? With billions of planets scattered across the Milky Way, the odds seem to favor the existence of another world like ours. But how do we find it? And if we do, what does it mean for our place in the universe? Join me as we embark on a journey to uncover one of the greatest mysteries of our time, the hunt for habitable planets beyond our solar system. For a planet to be considered Earth-like, it needs to be in a very special region around its star, a place called the Goldilocks zone, or the habitable zone. This is where temperatures are just right, not too hot and not too cold, allowing liquid water to exist on the surface. And water, as we know, is the key ingredient for life. Let's take our own solar system as an example. Earth sits comfortably in the Goldilocks zone, with oceans and a breathable atmosphere. Mars, on the outer edge, is too cold, with frozen water trapped beneath its surface. Venus, too close to the Sun, is a scorching wasteland, with temperatures hot enough to melt lead. But does this Goldilocks zone exist around other stars? And if so, how many planets could potentially be like Earth? The search for another Earth truly began in 2009, when NASA launched the Kepler Space Telescope. Kepler was designed to stare at a single patch of sky for years, looking for tiny dips in the brightness of stars, signs that a planet might be passing in front of them. This method, known as the transit method, allowed Kepler to detect thousands of exoplanets, many of them in the habitable zone of their stars. Among them, some of the most promising candidates were discovered. Kepler 22, b, the first confirmed planet in the habitable zone of a Sun-like star. Kepler 452b, often called Earth's cousin, a planet 60% larger than Earth, orbiting a star similar to our Sun. Kepler 442b, a rocky planet that could have conditions suitable for life. Kepler changed everything. Before its launch, we had no proof that planets like Earth even existed outside our solar system. Now, we know that there could be billions of them. But Kepler was just the beginning. Finding a planet in the Goldilocks zone is only the first step. To be truly habitable, a planet must have several key characteristics. 1. A stable atmosphere. Without an atmosphere, liquid water would either evaporate or freeze. Earth's atmosphere regulates temperature and protects life from harmful radiation. 2. The right chemical ingredients. Life as we know it depends on elements like carbon, oxygen, nitrogen, and hydrogen. 3. A magnetic field. Protects a planet from deadly solar winds and cosmic radiation. 4. A stable star. If a planet orbits a violent star prone to massive flares, its atmosphere could be stripped away. Some planets seem to have these conditions, while others, despite being in the habitable zone, may be barren wastelands. One of the biggest mysteries scientists face is how to distinguish truly habitable worlds from those that just look promising from a distance. Kepler gave us a glimpse of what's out there, but the real search has only just begun. Today, the James Webb Space Telescope is taking the hunt to the next level, using its advanced instruments to analyze exoplanet atmospheres. By studying the light that passes through these distant worlds, Webb can detect the presence of water vapor, oxygen, and even signs of life. In the coming years, missions like the Nancy Grace Roman Telescope, the European Extremely Large Telescope, and the Habitable Worlds Observatory will push the limits of our ability to detect Earth-like planets and, perhaps, even alien life. The question is no longer, are there habitable planets? But how soon will we find one? The evidence is mounting. Habitable planets could be more common than we ever imagined. But how close are we to finding an Earth 2.0? In the next part, we dive into the strange and fascinating worlds we've already discovered, some with oceans of lava, others with eternal night, and explore how scientists are narrowing down the search for the perfect world. Stay with us as we continue the hunt for another Earth. Not all planets are created equal. In our search for another Earth, we've discovered some of the strangest and most extreme worlds imaginable. Planets where it rains molten rock, where winds scream at thousands of miles per hour, and where ice burns instead of melts. Could a truly habitable planet be hidden among these strange worlds? Or are we looking for life in places where life as we know it simply can't survive? Join me as we explore the bizarre and breathtaking diversity of exoplanets and uncover the clues they offer in our quest for another Earth. One of the biggest surprises in exoplanet research is that the most common types of planets are ones that don't exist in our own solar system. Scientists have discovered super-Earths and mini-Neptunes, planets that are bigger than Earth but smaller than Neptune. Super-Earths can be rocky like our planet, but with stronger gravity and thicker atmospheres. Some may have vast oceans, while others could have crushing pressures that make life impossible. Mini-Neptunes are smaller gas planets, with thick atmospheres of hydrogen and helium. Some may have solid cores, but they're unlikely to be habitable as we know it. One of the most promising super-Earths is LHS 1140b, a rocky world in the habitable zone of its star. It's almost 7 times the mass of Earth and could have a thick atmosphere protecting a liquid water ocean. These super-Earths might be the best candidates for habitability, offering stable environments that could last for billions of years. But not all exoplanets are so welcoming. While searching for another Earth, we've found some of the most extreme and inhospitable worlds imaginable. 1. Lava planets, where it rains. Molten rock. Imagine standing on a planet where the ground glows like hot coals and raindrops are made of liquid rock. This is K2141b, a world where half the planet is an endless ocean of magma, and the other half is frozen in permanent darkness. Winds scream across the planet at thousands of miles per hour, carrying vaporized rock that falls as molten rain. 2. Ice giants. With burning ice. Some planets are so cold that their ice doesn't melt. It burns. Gliese 436b is a planet where ice is held together by extreme pressure so strong that it doesn't turn to liquid, even at hundreds of degrees Celsius. This exotic hot ice creates an entirely alien type of world, one that challenges everything we know about planetary science. 3. Planets darker than coal. Then there are planets that absorb nearly all light, making them darker than charcoal. TRES 2b, a gas giant, reflects less than 1% of the light that hits it, darker than the blackest paint on Earth. What makes it so dark? Scientists suspect that exotic chemicals in its atmosphere trap heat and light, making it one of the strangest planets ever found. Could life survive on such extreme worlds? Maybe not life as we know it, but what if alien life forms have evolved under conditions we can't even imagine? Water worlds, oceans beyond Earth. Visuals, planets covered in vast oceans, artist impressions of alien seascapes. Water is the key to life, and some planets we've discovered may be covered in oceans deeper and wider than anything on Earth. 1. GJ 1214 IB, the planet that might be an endless ocean. This world is larger than Earth, but smaller than Neptune, and astronomers believe it could be a planet-wide ocean with no land at all. If true, it would be one of the best places to search for alien marine life, deep under crushing waves. warmed by geothermal vents, like those found in Earth's deep oceans. 2. Europa and Enceladus, oceans beneath ice. Not all water worlds need to be warm on the surface. Some of the most exciting places to search for life aren't exoplanets at all. They're moons in our own solar system. Jupiter's moon, Europa, and Saturn's Enceladus both have vast oceans beneath thick layers of ice. These oceans could be warmed by tidal forces, creating the perfect conditions for life deep beneath the ice. If life can exist in the frozen depths of these moons, then life could also exist on exoplanets with similar conditions. Could an alien ocean be teeming with strange creatures, hidden from view under miles of ice? Among all the planets we've discovered, one stands out as the closest, most promising candidate for an Earth-like world. It's called Proxima b, and it orbits the nearest star to our solar system, Proxima Centauri, just 4 light-years away. What makes a planet habitable? It's not just about being in the right place. Temperature, atmosphere, and chemistry all play a role in determining whether life can exist. But how do we search for life from light-years away? In this part, we dive into the scientific methods used to detect habitable planets, from studying their atmospheres to searching for the telltale chemical fingerprints of life itself. Are we about to find proof that we are not alone? Let's explore the cutting-edge science behind the search for life. The first step in finding another Earth is identifying where to look. Astronomers focus on planets in the habitable zone, the region around a star where conditions aren't too hot or too cold, just right for liquid water to exist. For our Sun, Earth is in the perfect spot, but Mars is on the edge, possibly having had liquid water in the past. Around cooler red dwarf stars, the habitable zone is much closer, meaning planets orbiting these stars could be warm enough for life. The TRAPPIST-1 system, just 39 light-years away, has 7 rocky planets, 3 of which are in the habitable zone. Could one of these be an alien Earth? But just being in the habitable zone isn't enough. A planet needs more than the right location. A planet's atmosphere can make the difference between a world teeming with life or a lifeless wasteland. Look at Venus. It's almost the same size as Earth, in the inner edge of the habitable zone, but its thick atmosphere traps heat, turning it into a hellscape of 900 degrees Fahrenheit, 475 degrees Celsius. Mars, on the other hand, lost most of its atmosphere, leaving behind a cold, barren desert. To find another Earth, we need to study a planet's atmosphere from light-years away. But how? When a planet passes in front of its star, some of the starlight filters through its atmosphere. By analyzing this light using spectroscopy, scientists can determine what gases are present in an exoplanet's atmosphere, like reading a cosmic barcode. Certain gases could be signs of life. Oxygen and ozone. On Earth, oxygen is produced mainly by life. Methane, a gas that, when combined with oxygen, needs constant replenishment, possibly by life. Water vapor, a key ingredient for habitability. The James Webb Space Telescope is now scanning exoplanet atmospheres for these chemical fingerprints. If it finds oxygen and methane together, it could be the first evidence of alien biology. One of the most promising targets is K218b, a planet 120 light-years away, where astronomers recently detected water vapor. Could it be habitable? Beyond detecting gases, scientists are searching for biosignatures, chemical or physical signs of life. One of the most controversial findings came from Venus in 2020, when astronomers detected phosphine in its clouds. On Earth, phosphine is made mainly by microbes, but the discovery remains uncertain and raises a bigger question. What if alien life doesn't follow Earth's rules? Some scientists propose that life could exist in strange forms. Silicon-based life instead of carbon-based. Life that thrives in extreme environments, like acidic clouds or methane lakes. Microbial life hidden under ice or deep underground. The discovery of extremophiles, organisms that survive in Earth's harshest conditions, suggests that life could exist in ways we never expected. But what about intelligent life? How do we search for civilizations beyond Earth? While biosignatures hint at primitive life, technosignatures look for intelligent civilizations. For decades, the search for extraterrestrial intelligence, SETI, has been listening for radio signals from distant stars. But modern astronomers are looking for other technosignatures. Artificial light pollution on exoplanets. Unusual heat emissions that could indicate cities or industries. Megastructures like Dyson spheres. Huge constructs that could surround a star and collect IIE. We've found planets that could be habitable. We've detected water, oxygen, and even possible biosignatures. But what happens next? If we discover an Earth 2.0, how do we get there? Can we send a probe across light years of space? And if we detect intelligent life, are we ready for first contact? In this final part, we explore the future of interstellar travel, colonization, and the possibility of communicating with alien civilizations. The biggest challenge in reaching an exoplanet? Distance. Our closest star system, Alpha Centauri, is 4.24 light-years away. That means even at the speed of light, a message would take over 4 years to reach it. The fastest spacecraft ever built, Voyager 1, travels at 38,000 miles per hour, 61,000 kilometers per hour. At that speed, reaching Alpha Centauri would take over 70,000 years. Even Proxima Centauri b, an exoplanet in our nearest stellar neighborhood, remains out of reach with current technology. So how do we solve this? Scientists are exploring new ways to break the speed limit of space travel. To reach another Earth, we need a revolution in propulsion technology. Here are some possible solutions. Nuclear fusion rockets. Using the same reaction that powers the Sun, fusion rockets could reach 10% the speed of light, cutting travel time to Alpha Centauri to just 40 years. Light sail technology. Projects like Breakthrough Starshot propose using powerful lasers to push tiny spacecraft at 20% the speed of light, reaching Alpha Centauri in 20 years. Warp drives. Inspired by Einstein's equations, scientists are exploring ways to bend space-time, creating a shortcut through space. Though still theoretical, NASA researchers are investigating Alcubierre drive concepts. If we develop one of these technologies, humanity could become an interstellar civilization. But before we send people, we'll likely send robotic probes to scout ahead. The first step in exploring an exoplanet will likely be an AI-powered robotic mission. A next-generation Voyager probe built to analyze an alien world up close. A future probe could map the surface in high detail, analyze the atmosphere for biosignatures, detect water, vegetation, and possible life forms. If a robotic mission finds strong evidence of life, the next step could be sending humans. This raises a profound question. Should we colonize another Earth? If we find an Earth-like planet, should we move there? Some scientists believe colonizing another world could ensure the survival of humanity. Stephen Hawking once warned that humanity must become a multiplanetary species to avoid extinction. But settling another Earth is easier said than done. Would the atmosphere be safe to breathe? Could we grow food there? Would there be unknown alien life forms, friendly or hostile? One ethical dilemma looms over colonization. What if there's already life there? Do we have the right to alter another world? History has shown that exploration often comes with unintended consequences. What if human arrival disrupts an alien ecosystem? But what if we don't have to go to another Earth? What if another Earth comes to us? For decades, scientists have searched for radio signals from intelligent civilizations. If we detect a message from an alien world, what should we do? Some scientists argue we should respond immediately, opening communication with an alien race. Others warn that contacting advanced civilizations could be dangerous. Physicist Stephen Hawking cautioned, "If aliens visit us, the outcome could be much like when Columbus landed in America, which didn't turn out well for the Native Americans. But what if aliens are already watching us, waiting for us to reach a certain level of technology before making contact?" Some theories suggest that Earth could be part of a galactic quarantine,